All right, so the first light sensor we're going to talk about is a photodiode, which is a semiconductor device that converts an optical signal into an electrical signal. Now, here again, I'm sure the students have used a PN junction type device before. Now, in a normal PN junction, obviously, you have a barrier, right? And normally on the N type you have electrons, right? And on the P type you have holes, right? They move to opposite sides, creates a what you call a depletion region. Now, when you apply a biased field, right? This is just a normal PN junction. It becomes smaller, right? So your resistance decreases. Now, normally what happens is if you do that after some time, right? Obviously your electrons from the N type will go to the P side, and the holes will go to the other side, and it will fill the holes and the electrons, right? And then there'll be no more free carriers left.
Only ions will.
Only ions will be there, and that ions then creates what?
Some electric field.
Yes. So there's some built-up electric field, right? Where there are no more charge carriers, so there's no current flow. And now, when we expose this,
That junction
to
sunlight,
or any kind of light, what happens is it creates these electron hole combinations, and obviously your holes, and then you reverse bias this photodiode so that your electrons will flow to the plus side, right, and your holes will flow to the minus side. So you have what you call a photocurrent, right? And that is because these incident photons, they carry some energy, right? And even though this electric field, there are no charge carriers, these can move certain electrons from a valence to a conduction band, and then you have free carriers. So when there's no light, right, I0.
What is this curve?
This is an IV curve.
Of that junction.
Of that junction, right, of this photodiode, right? Now, obviously, this junction is sensitive to light, and you want this junction to be large as possible, so a lot of light could be attracted. Now, when there is no current, right, we call this a dark current. Now, when there's no light.
Yeah.
Now, when the light increases, right, you can see a very clear shift.
That dark current increases.
The dark current increases, and in fact, it increases.
So the whole VI or IV characteristic is shifted down,
and that's shifted down linearly. Okay, so depending on the amount of light, right, this photodiode kind of the current decreases in the circuit.
Just a moment. Now, the curve also passes through the fourth quadrant.
Sorry, third?
The curve,
yes,
is also passing through the fourth quadrant.
Fourth quadrant? You mean here?
No. That's the third. So the photodiode is in the third quadrant. No, first quadrant is normal diode.
Yes, this one.
Top.
Quadrant 1.
Quadrant. Yeah. I mean, where current and voltage are positive.
Forward bias.
That is normal diode.
Yes.
It is like a photodiode in the third quadrant, where voltage where the voltage and current are negative.
Yes.
Now there is also a fourth quadrant where voltage is positive but current is negative.
Voltage is positive, current is negative. Yes.
That's also a device. We will ask the students to find out.
Okay. Right.
Yeah.
All right. Now, so what we talked about before was a photoconductive mode diode. Now, the sensitivity of this diode is equal to this, right? IP is your photocurrent due to this incident photons, and P, which is equal to RP-HV. Now, HV is the energy of a photon, and RP is basically the number of photons hitting this junction per second. Now, there's also another one called a PIN photodiode. What's the difference between a PIN and a PN photodiode?
What is I stand for?
I is good point. I think it's called an interfacial layer, intrinsic region, which we choose, right? What that means is here, the depletion layer, that size depends on the bias voltage. Right? Here, it does not really depend on bias voltage. It's something that we fix when we manufacture the device, right? And it's usually made of some undoped or lightly doped semiconductor. Now, this has very high resistance, generally. And so this increases the built-up electric field. And again, as I said, it's independent of the bias voltage. Now, they also have faster response times due to the wide intrinsic region. Because that reduces the capacitance of the circuit. So that's another way. I think this is the most widely used type of photodiode, right?
For high-speed applications.
For high-speed applications, and it's also quite sensitive because the region is also quite large, so you can attract more photons. There's another photodiode called photovoltaic photodiode. There is no bias voltage, right? Now, so this dark current, right, will be very low, which means in these cases there is some dark current which could be, which is considered some kind of a noise. But because this doesn't have a bias voltage, doesn't have a dark current, so there's very low noise. Now, again, basically the idea is the same. When there is a photons hitting the junction, some voltage is created. Now, because this does not have a bias, right, the capacitance of this is at a maximum, right? So it's very slow to respond. So that's the disadvantage of this photovoltaic photodiode. Now, photodiode has many different applications. Of course, in medical devices, you can measure blood oxygen levels, medical imaging, optical fiber communication, data transmission, proximity sensing, also used in spectrometers to analyze light spectrums, digital cameras and scanners. So really a lot of different applications use these photodiodes.